Okay, ma'am. Good afternoon, everybody. Welcome to GATE online classes in civil engineering, particularly the concrete structures subject. And in the last class, we have seen some fundamental concepts related to the limit state method of design. Now let us continue the same topic. In the last class, we have seen up to find how to find out the characteristic compressive strength of concrete, characteristic load, and what is the acceptance criteria, and how the strength values are obtained based on the variation of the standard deviation. So let us have a brief look once again regarding the characteristic load. Characteristic load is the value of the load which has 95% of the probability not being exceeding during the life of structure. So you know W bar is the average load, WCK is the characteristic load. That means below this value, 95% of the probability exists. So in this white area, 95% of the probability, and the hatched portion is only 5% of the probability of exceeding the loads. So here what is going to happen in this particular case, the characteristic load is always more than the average load. And already I have seen another one, characteristic strength. Characteristic strength is always less than the average strength. So in case of strength, we are giving factor of safety by reducing the stresses, whereas in case of loads, we are giving factor of safety by at the ultimate loads, and it has 95% of probability of not being exceeded. So in the last class, we have seen the concepts up to this, and also the numerical problems regarding the characteristic load and also characteristic strength. Now let us move to another one, continuation, partial factors of safety. So in working stress method and limit state working stress method and ultimate load method, factors are considered only for material in one case, only for the load in another case, and the justification of the theoretical concept is not correct, and those two theorems are methods are invalid, and this is the limit state method is the important method which consider the safety of the structure and also the serviceability requirements. So factors of safety is given both for the materials and also the loads. So safety of the structure is by means of introducing partial factor of safety for materials and partial safety factor for the loads. Now let us have a look for materials. FD is the design strength, whereas F is nothing but the characteristic strength divided by gamma m. Gamma m is the partial safety factor for the material. So here material means two different types of materials. One is concrete, another one is steel. So for concrete, factor of safety is 1.5, and for steel the value is 1.15. That we'll see in the next page. And similarly, characteristic loads. Characteristic loads will be obtained by multiplying the actual loads. The design load will be equal to the characteristic load multiplied by the factor of safety. So here the factor of safety is involved for multiplication of the characteristic load, whereas in case of materials the stresses are reduced. So stresses are reduced in the materials, whereas in the case of loads, ultimate loads are considered by multiplying the factor of safety. So here factor of safety is for different types of loads. In general, this is the equation FD equal to gamma F multiplied by F characteristic load. And here what are the different types of loads in normal way? Dead load, live load, wind load, earthquake load. These are the major loads that normally coming on the structure. And of course some special cases of the structure, other loads may also be considered for the analysis and also the design. So here according to the nature of the load, the gamma F value varies. So here in this particular case, you can look at here the factor of safety for material is taken into account by considering the deviation of the strength of material, because normally strength of material never be uniform throughout the length in a particular member or in different cases, and accuracy deficiency in calculation procedure and risk to life and economic consequences because of this factor of safety is being introduced for the material. And similarly, the factor of safety for load will be accounted by considering the various factors, that is unusual increase in load beyond that used for deriving the characteristic values. So sometimes characteristics values may be obtained based on the probabilistic theory and statistical analysis. Sometimes that analysis may be some deviation and unusual expectation of the increase of the load beyond that calculation may occur, or otherwise unforeseen stress distribution. Stress distribution may not be expected way, it may be in a different way, or inaccurate measurement of the effect of loads assessment may be wrong sometimes, or importance of the limit state considered. So because of these factors considered, the factor of safety must be used for the characteristic load, so that ultimate load will be obtained. So here what we are doing, ultimate load is for the safety purpose, and factor of safety for material is used for the serviceability requirements. So both the requirements will be satisfied in the case of limit state method of design. And these are the appropriate codes for dead load, live load, wind load, and also the seismic load. Now, what are the various partial factors of safety for different materials and also the different loads? And in general, partial safety factor for load is 1.5. If nothing is mentioned, and in general, for dead and live loads are the common loads that we use for all computations. And in some special cases, the wind forces also coming into picture, and earthquake load also coming into picture when it is considered in the design. So otherwise, normally for dead load and live load, it is 1.5 times. So gamma F is 1.5. So that means if you multiply the characteristic load by 1.5, you will get the design load, or otherwise it can be called as factored load, or otherwise it can also be called as ultimate load. Ultimate load, factored load, design load are one and the same. And similarly for the materials, concrete partial factor of safety is 1.5 and steel is 1.15. So these values are fixed. For concrete, whatever may be the grade of concrete, gamma m is 1.5 for concrete, and for steel it is 1.15. And again, there is a variation of factor of safety for concrete and steel, because the steel is manufactured from the standard manufacturing unit under strict quality control. So the variation of the stress in steel is very less, and we are using low partial factor of safety. Whereas concrete is being having a lot of degree of variability. Degree of variability is more, and more variations are possible, and deviation of the strength depends on the several factors right from materials, manufacturing, transportation, placing, compaction, curing, etc. All the factors are there. So that's why gamma m is a higher value 1.5. And sometimes in normally majority of the examinations, the questions will be what is the partial factor of safety for concrete in limit state method, or simply what is the value for steel. So such a simple questions will also come in the examinations sometimes, several times. And this is regarding the materials. Materials, these two are constant. Whereas for the loads, in general for dead load and live load, it is 1.5. But if we look at combination of all the different possible loads, normally three different possible combination of the loads are to be considered, and accordingly the worst load will be considered for the design. So here the load combination is dead load and live load. And in almost all the structures, the dead load and the live loads will be acting normally, and both will be multiplied by 1.5 and 1.5. 1.5 and 1.5, so that you will get the collapse load, and accordingly design it for limit state of collapse. Or sometimes wind load is also there, then you have to look for one more combination, either wind load or earthquake load. Either wind load or earthquake load. Only one of these two will be considered for the combination of the load. Dead load plus wind load, or otherwise dead load plus earthquake load. That means consider only wind load or earthquake load, whichever is more. Consider one of these two, whichever is more. In that case, dead load is multiplied with 1.5, wind load also multiplied with 1.5. And sometimes there is a possibility of reversal of stresses, reversal of stress because of the dead load. So because of the dead load in a particular beam or a particular phase, tension occurs. And because of the wind load, the same phase will be under compression. That means a change of the stresses at a particular section, particular line will change. That is reversal of the stresses. Initially, one nature of the stress will be changed to another nature of stress. In such case, the dead load is multiplied with 0.9. It will be clearly mentioned if this is the special case. In the examination, if there is a question, if the reversal of stresses takes place, then only dead load is multiplied with 0.9, otherwise it is multiplied with 0.5 only. And another combination, dead load, wind load, and also live load. Either wind load or earthquake load. Consider only one of these two, whichever is maximum. Whichever is maximum. And when all the three loads are considered, and all the three may not always act, all the three may not act full, so it will be reduced to 1.2, 1.2 and 1.2. So you need to remember this 1.2 factor if all the three loads are present. Otherwise, it is multiplied with only 1.5, except one case where the reversal of stresses takes place. When the reversal of the stresses takes place, dead load is multiplied by 0.9. Otherwise, 1.5 in general, when all the three loads are acting, it is with 1.2 coefficient, 1.2 factor, load factor. And it is the case of limit state of collapse. Limit state of collapse means if it is to be designed for bending, shear, torsion, compression, then those moments or loads are multiplied with these factors. And another limit state is limit state of serviceability. So at the serviceability, the loads are considered as service loads. Service loads means actual loads. Service loads means actual loads. So here you can look at everything is one only. Everything is one only means it is actual loads only. So the loads multiplied by factor 1, so that it is the actual loads or simply the characteristic loads acting on the structure. But when the combination of dead load, live load, wind load occurs, Dead load is permanent, which will be there along with the structure. There is no change in dead load. So that's why it will be taken 1. And all other loads, because full live load and full earthquake load or full wind load may not occur. So these values are reduced to 0.8. So you need to remember when the combination of all the 3 loads are acting, for collapse it is 1.2, for limit state of serviceability, dead load there is no change, and other loads it will be multiplied by 0.8. So in that way, you should keep this table in your mind, because sometimes the numerical questions may be asked basing on these coefficients, these factors for limit state of collapse and limit state of serviceability. So once again, I am telling you, in the case of limit state of collapse, the loads are multiplied by 1.5 in general. Very exceptional case where the reversal of stresses takes place, dead load is multiplied by 0.9. When all the 3 loads are combination occurs, then it will be reduced to 1.2. All are multiplied by 1.2 only. In case of serviceability, service loads will be considered. Service loads means actual loads will be considered in first 2 cases. When all the 3 loads are acted together, full service load for dead load and 80% for live load, 80% for the wind load will be considered for the computation of the ultimate loads. And here just in the explanation to that one. Already you have seen when there is a reversal of stress, 0.9 is taken. The value of 0.9 is considered when stability against overturning or reversal of stresses takes place. Okay. For limit state of collapse, design loads are considered. For limit state of serviceability, actual loads are considered. So in limit state of collapse, design loads means load multiplied by partial factor of safety. And in limit state of collapse, only the actual loads except the combination of all the 3. Wind load, earthquake load, both may not occur simultaneously. Maximum value of wind load or W load, the wind load or earthquake load is considered. So both wind load and earthquake load may not occur simultaneously. So that's why the chances of it will be very rare and it is almost impossible. And maximum value of either wind load or earthquake load is considered for computation of the loads. And increase in permissible stresses. Where stresses due to wind load, earthquake load, temperature effect, shrinkage effect are considered, those due to live load and dead load, the stresses specified may be exceeded by 33%. Because when you consider wind load, effect due to temperature, effect due to shrinkage, all these into account, the permissible stresses are reduced by reduced by 33.1 percentage. That means 33%. Now let us look at numerical problem basing on the loads, basing on this particular table. Sometimes the numerical question may be asked. You can look at the member in a structure is subjected to dead load 100 kilonewton meter, live load 160 kilonewton meter, wind load 80 kilonewton meter, earthquake load 120 kilonewton meter. The question is, what is the design load for limit state of collapse? What is the design load for limit state of collapse? In the previous table, you have seen there are 3 different combinations. For these 3 different combinations, calculate the collapse load, or factored load for each of these 3 cases and consider the maximum. Okay, so here you can look. The design load for collapse is the maximum of the following combinations. There are 3 combinations. What is the first combination? Dead load and live load combination. When dead load and live load only considered, the factor will be 1.5. So 1.5 into dead load plus live load, 1.5 into what is dead load? 100, and what is live load? 160. So this is 390. So that means factored load by considering the combination 1 is 390 kilonewton per meter. And in the second combination, dead load and wind load combination. So I told you wherever the term wind load exists, you take only the maximum of wind load and earthquake load. Which one is maximum? Wind load is 80, earthquake load is 120. Consider one of these two, that to maximum value. What is that maximum value? Wind load is not maximum, earthquake load is maximum. So consider the earthquake load in place of wind load. So that is 1.5 dead load plus wind load or earthquake load. So either you consider with wind load or earthquake load, whichever is more. But earthquake load is more. You are considering 120 as earthquake and dead load is 100. So it will be 330. So the factored load for the second combination is 330 kilonewton meter. And similarly, the third combination, dead load, live load, wind load are present. Then the factor for all these loads will be 1.2. 1.2 times of dead load, live load, and also earthquake load. Here wind load or earthquake load, but the earthquake load is more. You are considering earthquake load into account. So 100, 160, 120, 456. So these values are simply basing on 1.5 and 1.2. If you are able to remember what is 1.5 factor, what is 1.2, then you can find out these three combinations. What is the collapse load now? Collapse load is greater of these three. So 390, 330, 456. So collapse load will be 456 and this will be the answer. This may be a question in the examination without taking much time. You need not write all those things in the exam. So you just multiply the last one. So this is the only important part, and simply this is the only important point. This is another important point. It will take very less time. But it is for giving the explanation, I have written everything clearly to understand the things. Okay. So this is a simple procedure for computing the collapse load of limit state of collapse. Collapse load for combination of various loads. And for the same loads, the second question is the design load for serviceability is. The design load for serviceability is. So what you should understand now, for serviceability, what are the coefficients, factors? It is 1 for in general and 0.8 for live load and also wind load when all the three loads are considered. So you need to understand the various factors for the serviceability in this table. Now look at this. Design load for serviceability is maximum of the following combinations. Combinations are same. First combination is dead load and live load combination, and factor is 1. So 1 into 100 plus 160, 260. That is one combination. And dead load and wind load are considered. Wind load means it is either wind load or earthquake load, whichever is maximum. Here earthquake load is maximum, it is 120. So again 1 into 100, 120, 220 kilonewton meter. Units are wrong, it is kilonewton meter. When all the three loads are present, you can see dead load is multiplied with 1, live load is multiplied with 0.8, and earthquake load or wind load is multiplied by 0.8. So accordingly, 1 into 100, 0.8 into 160, 0.8 into 120, you will get the third value. So out of all these three, The maximum value is 324. So design load for serviceability is to be considered as 324 kilonewton per meter. So this is how sometimes you need to solve the numerical problems in the examination. Such a simple questions, concept based questions will appear in the examination. Now let us go in deep regarding the limit state of collapse. The limit state of collapse, now let us go for the flexure. So that means flexure means the design of a structure for bending. Design of a structure for bending. So these are the assumptions that are taken from the IS code, because IS 456 is the only base for the complete design of RCC. And each and every word of some of the things are a replica of IS 456. It will be taken from IS 456 only. But the explanations are a bit different. Those things are not there in the IS 456. For example, the first assumption is plane sections normal to axis remains plane after bending. Already in working stress method also you have seen this one. That means you can look at this section before bending, the member is straight and the section is clear vertical, it is plane. And after bending, the same section will take the shape like this, take the shape, and at that plane, the section may not be perfectly vertical or perfectly same as that of the original. So in that case, we are assuming that the plane before bending, plane after bending at the same point is the same. That is the first assumption. This is mainly because of the stress at any point on the cross section is directly proportional to its distance from neutral axis. That means if you draw the strain diagram, this is the strain diagram. The strain diagram across the cross section varies linearly. For this purpose, the assumption 1 is mentioned in the IS 456. So plane sections remain plane after bending means the strain varies linearly across the cross section. Strain varies linearly across the cross section. That is the first assumption. And here, of course, stress is proportional to strain also. Number 2, maximum strain in concrete at the outermost compression fiber is taken as 0.0035 in bending. So you can look at here, strain in concrete, assume that it is simply supported. Assume that it is simply supported. If it is simply supported, bottom face is under tension, top face is under compression. So the maximum value of the compressive strain at the outermost compression fiber is taken as 0.0035. So this value also important from the examination point of view. Okay, and concrete is a brittle material and gets crushed in compression at low strain of 0.0035. So it's a brittle material and strain is also very low and it will fail at that point. We consider only the strain up to 0.0035 only. Beyond that, we are not going to consider the strain in the analysis. Third assumption, the relationship between compressive stress distribution in concrete and strain in concrete may be assumed to be rectangle, trapezoidal or parabola or any other shape which results in prediction of strength in substantial agreement with the result of the test. So here the meaning of it will be in general for a concrete the stress strain diagram is a non-linear curve like this. Non-linear curve is like this. And it is approximately linear. It is also not linear. It's approximately linear up to 10 to 15% of the ultimate value. So you can look at initial line is approximately straight line, but originally it is also not a straight line. If the variation of the concrete stress strain diagram is always nonlinear, and approximately 10 to 15% of the ultimate value, the line varies approximately straight line, and beyond that it is non-linear. Beyond that it is non-linear, and as a whole it is completely non-linear variation only. Non-linear variation only. And normally, what is going to happen here in the concrete, particularly in the concrete, the cubes are to be tested for 150 size. Cubes are tested for 150 size for the strength of the concrete. But in the field, the strength, the size of the member is not 150 by 150. So this is the laboratory testing of the cube compressive strength, and basing on that we are going to evaluate FCK, characteristic strength of concrete. And whatever the strength that is obtained for 150 cube is not exactly to the practical field, because to the practical field the size of the member is more than 150. The size of the member is more than 150. If the size of the member is more and more, the compressive stress is decreasing. If the size of the member is more, compressive stress is decreasing. And as the size of the member is more and increasing from 150 to 450, the value is continuously decreasing up to 450, and thereafter the decrease is very small and hence neglected. So what normally we do is up to 450 size of member, the stress is approximately equal to 2/3 of FCK, because for 150 it is FCK. For 450 it is nothing but 2/3 FCK, and most of the members in practice are larger in size than 150 size of the cube. So that's why the strength in practice is reduced to 2/3 of FCK, and it is 0.67 times of FCK. So because of the size effect, the reduction in the strength of the concrete taken as 0.33 FCK. Reduction in strength of the concrete taken is 0.33 FCK. But the value considered for the practical condition 0.67 times FCK. And now design compressive stress. This is the characteristic strength considered, and what is the design value? Design value is nothing but characteristic value considered by factor of safety for material. And since it is concrete, factor of safety is 1.5, so you will get 0.67 by 1.5 is 0.45 FCK. 0.45 FCK. So that means we are going to consider here the strength of the concrete as 0.45 FCK after considering the size effect and also the introduction of the partial safety factor for concrete. Partial safety factor for concrete. For example, if there is no partial safety factor, what is the strength to be considered? It is only 0.67 times FCK. If size effect is also not considered, what is the value of the design value? FCK. So FCK is originally the characteristic strength, and because of the size effect, it is reduced to 0.67 times. Reduced to 0.67 times FCK, and by the introduction of the partial factor of safety, the value becomes 0.45 FCK, and finally we are going to use compressive strength. Maximum compressive stress in concrete is considered as 0.45 FCK only. Is considered as 0.45 FCK only. You can look at this stress strain curve. In the original stress strain curve, you can look at we consider up to certain level, and after that it will be taken as horizontal. After that it will be taken as horizontal, and corresponding stress will be equal to FCK. So that is considered ideal. Stress diagram is considered initially parabolic in shape, and once it reaches certain value, then it is horizontal, because at the strain of 0.002, at the strain of 0.002 in concrete, the first micro crack will develop. The first crack will develop at this particular strain, and once the cracks developed, then it may not take much load and it is going to deform further, and additional increase of stress is not taken into consideration. Additional stress is not taken into consideration, so it will be taken as horizontal. That means the maximum stress is achieved at 0.002 strain, 0.002 strain maximum value is achieved, and after that it will be considered as constant, and that is constant up to 0.0035. In the second assumption, you know that maximum compressive strain in concrete is taken as 0.0035. So beyond that, if there is a strain, that we are not considered and we are neglecting. We are assuming that the entire concrete is going to fail by attaining 0.0035 strain. And when strain is 0.002, first crack will develop in the concrete. So first crack will develop in the concrete, and the at 0.0035, the entire concrete will gets in collapse condition, collapse stage, failure stage. So originally in the first curve, you know that it is FCK. That means based on the laboratory condition. Based on the laboratory condition, FCK is taken. And based on the field condition means the size effect. Size of the member is more than the size of the cube tested in the laboratory. So FCK by 1.5, it is not actually FCK by 1.5, it is 2/3. We should not write like this. It is actually 2/3 of FCK, or otherwise 3/2 means 1.5. 1.5. 2/3 of FCK, 0.67 FCK. And this is field condition. And after introducing the partial factor of safety 1.5, you will get 0.446 FCK, or otherwise it will be taken as 0.5 times of FCK. So in general, what we are going to do is, we are going to consider ultimately, this is the stress diagram for concrete. This is the stress diagram for concrete. Stress diagram for concrete is initially zero stress, and it is varying parabolically. This ordinate is 0.45 FCK. This is 0.45 FCK, and it is constant for another distance of 0.0035 strain. When it will be zero stress, normally when it will be zero stress will be occur only at the neutral axis. If you consider that this is the neutral axis, if we consider that this is neutral axis, so zero stress for concrete, and it is increasing parabola, up to the strain of 0.002. And after that it will be a rectangular in nature. In nature. So parabola and rectangle. So you know that here what is the distance of the parabola? Distance of the parabola is 0.002. Distance of the maximum value is 0.0035. So you can consider this as 35. 35 means you can call it as 7 parts. 7 parts. Each part is 5. So how many parts up to here? 7 parts. 7 into 5, 35. How many parts here? 5 into 4. 5 into 4. So 4 parts here. Overall is 7 parts. So that means you can call it as 4 parts and 3 parts. In a overall depth of this will be considered as 4 parts of parabola, 4 parts of height of parabola, and 3 parts of rectangular, because you know that 0.002, whereas it is 0.0035. So here 4 times, and whereas it is 3 times, the total is 7. The total is 7. And when you call it is neutral axis, normally the depth of the neutral axis is called the XU. Depth of the neutral axis is XU. So what is the top distance? What is the top distance? 3 parts out of 7 parts. So you can call it as 3 by 7 of XU. And what is the parabola height? 4 parts. 4 parts means this distance will be equal to 4 by 7 of XU. So when XU is the depth of the neutral axis, that is distance of the neutral axis from the top extreme fiber, extreme compression fiber, and it is 3 parts and 4 parts. So you know rectangular height is 3 by 7 of XU, and parabola height is 4 by 7 of XU. So this is how you can represent the height of rectangle in terms of neutral axis depth, and the height of parabola represented in terms of the depth of the neutral axis. Okay. Now look at another point, another assumption in the code. The another assumption is tensile strength of concrete is ignored. So already in the earlier case also you have seen that entire tensile strength of the concrete is neglected. If this is the steel reinforcement and it is neutral axis, so this entire area is not considered, only concrete area is considered on the compression phase, already discussed in the earlier class. The cracked concrete does not contribute towards enhancement of moment of resistance, because on the tension phase, the nature of the stresses are tensile. The nature of the stresses are tensile. When the tensile stresses are developed, and naturally the cracked section, micro cracks may form in the bottom of the neutral axis, and once it is a cracked concrete, it may not contribute any moment of resistance of the section, and that's why the effect of this will be completely neglected. Only the steel reinforcement is considered for the only steel reinforcement is considered for the tensile stresses that are being taken up. Then another one, another assumption: the stresses in reinforcement are derived from representative stress strain curve for the type of steel. Stress strain curve for the type of steel. So what are the different types of curves that you know? This is called the mild steel. Originally, already in the previous section, previous working stress method, you have seen what is the stress strain diagram, original or actual stress strain diagram for mild steel. And similarly, what is the actual stress strain diagram for HYSD bar. Now, these are the diagrams idealized as per the IS 456. So in case of mild steel, this is mild steel, or otherwise you can call it as Fe 250 grade steel. The up to certain point it is linear, and afterwards some curve will be there, and neglect that once it yields, and it will be taken the same magnitude till its failure. That is called Fy. Fy is now characteristic strength of the steel. Now, what is this line? For the characteristic strength, what is the design strength? Design strength will be characteristic strength divided by partial factor of safety, that is 1.15. Ultimately, you will get 0.87 Fy. In all the major formulas, we are always using in limit state 0.87 FYAST, something like that. 0.87 FYAST, how you got it? You got it only FY divided by 1.15. That means introduction of partial factor of safety for steel, so that you will get 0.87 times of FY. And here there is a definite yield stress. There is a definite yield stress. And in case of HYSD bar, there is no definite yield stress. There is no definite yield stress. And yield stress is always corresponds to 0.2% of the strain, because it is a curve. Initially it may be straight line, and afterwards it is a curve. There is no specific or definite point of yield stress. So yield stress will be obtained corresponding to 0.2% of the strain. So put the 0.2% strain at this point and draw this line parallel to the original line, parallel to the initial original line. This is initial original line, and to that draw this parallel line. It will touch this point, and that will be called as Fy, and it will be taken constant Fy value. And after introduction of the partial safety factor, it also becomes 0.87 times Fy. It also becomes 0.87 times Fy. So here you can look at, for the design purposes, partial factor of safety for steel 1.15 shall be applied. So what is design stress? Fd equal to Fy by 1.15, it is 0.87 always. And for M25 to 250 M for Fe 250 grade steel, design value will be 0.87 times 250. You know it is 0.87 Fy, 0.87 into 250, 217.5. So that means we are considering in the design, or we are limiting the stress in the mild steel is only 217.5 Newton per mm square. At that stage, what is the strain? Strain at yield stress. What is the strain at that yield stress? Strain at yield stress. Yield value means 250. So Fy by Es is the strain, and 250 by modulus of velocity for all the steels is same. 2 into 10 power 5 Newton per mm square. So the strain at yield stress is 0.00125, whereas the strain at design yield stress. What is design yield stress? Design yield stress is now 217.5. So consider that stress value here. 217.5 means 0.87 into 250 divided by this, and this is 1.00109. That means at a strain of 0.00109, it reaches its design stress value of 217.5. So this is the maximum strain that occurs in the mild steel reinforcement. Maximum strain occurs in the mild steel reinforcement is 0.00109. Similarly, here what is going to happen? Yield strain is always more than the yield strain at the design stress. So always consider Fd equal to 217.5. Fd equal to 217.5. So that means in the steel reinforcement, the stress completely depends on the magnitude of the strain. It completely depends on the strain. For example, in the mild steel, if the strain is 0.00109 or more, 0.00109 or more, then the stress value will be equal to 217.5. If the strain is less, than this, naturally the stress will also be less. So in steel, the stress completely depends on the amount of strain in the steel. Similarly, for Fe 415 grade steel, for Fe415 grade steel. If you look at in the diagram, you will get several values in the IS456. Those values are drawn like this. So several values are drawn in IS456 in this way. That is for different design stresses. Different design stresses means you can look at different design stresses means it is shown zero point 0.8 times of FD, 0.85 times of FD, 0.9 times of FD, 0.95 times of FD, 975 of FD, and also FD. So for IS456, because the strain and stresses are completely dependent, these are the values given in IS456. The stresses. What is FD here? First one means 0.8 times FD means what is FD? 0.87 times FY. 0.8, 0.87, 415. That is the meaning of 0.8 times of FD. So here you can look at strain at stress of 0.8 times of FYD. So yield stress for the design or otherwise design yield stress of 0.8 times is strain equal to that stress value by modulus of velocity. It is 144. It is 144. 0.00144. And similarly, strain at yield stress of 0.9 FYD. You put here 0.9 and write it, and the initial strain will be 0.003 and it is 0.00192. Similarly, corresponding to FYD, the value is 0.00380. 0.00380. So sometimes one of the calculation of any value may be important in the examination, or otherwise for understanding this. In particularly Fe415, you cannot take the stress always 415 Newton per mm square. The stress in the steel in a section completely depends on the magnitude of the strain. Completely depend on the magnitude of the strain. If the strain is 0.00380 or more, then the design stress will be 0.87 times 415. If the strain is any other value, you can see the lower value of the strain, still lower value of the strain. Naturally, stress in steel is also less. Stress in steel also less. I will show you the values. So you can observe here, these are the design stress, 0.8 times FD, and it is Fe415, 144 and 192 already calculated earlier. You can look at 0.00144, 0.00192, this is for 0.8 and 0.9, and 380 is for one time. So you can look at here 380, 144, 192. So this is how the strain values are computed for Fe415. What is the corresponding stress? 288.7. How you got it? How you got this value? That value is level of stress is 0.8. So 0.8 times FYD. What is FYD? It is 0.87 times 415. If you multiply this, you will get 288.7. So that means you will know the stress value and also the strain value. So that means stress is always not equal to its maximum value. Stress is always not equal to the maximum value. It always depends on the amount of strain that the bar undergoes. The amount of strain that the reinforcement undergoes, the magnitude of the stress will be acting on it. Similarly, 1 into FD means, what is 1 into FD? 1 multiplied by 0.87 multiplied by 415, which is nothing but 360.9 Newton per m square. So this is the design value corresponding to 0.00380. And for all lower strain values, the stress you cannot consider full value. It will be some reduced magnitude of the stress. And similarly, the same type of calculations for Fe 500 grade steel also. For example, for 9 times FYD, 9 times 0.87 into 500. So it plus the strain, it is 226. You can look at here in the table. Here this is 226. Accordingly, the stress values. So don't by heart any of these things, not required. So whenever some question arises for computation of the strain or stress, you know how to calculate the strain values at this level. 0.9 times of F design stress means, yield design stress means 0.9 times of yield stress divided by modulus velocity, you will get the strain. This is how the strain in a reinforcement is computed. Okay, this is a table. Don't remember any table. All these values you can derive based on the previous calculations. You can see here how you got various magnitude of the strains and also the stresses. That is this table. Don't remember any of the value, not required. Next, sixth assumption: the maximum strain in a tension reinforcement in the section at failure shall not be less than. So that means, you know, the strain diagram is like this. So this is the neutral axis. It is a strain in concrete, and this is strain in steel. So the meaning is strain in steel not less than. So at the bottom, at the time of failure, the strain should not be less than this. That means sometimes it may be under reinforced section where steel may fail, and it may be over reinforced section where concrete may fail. Irrespective of concrete fail or steel fail at a particular section, the strain should not be less than this. Why this assumption is considered? Why this assumption is considered? Because when the strain is not less than this value, the ductility property of the whole section will be more. Ductility property will be more. So because of providing the ductility property, the failure is always associated with the steel reinforcement. Even in under reinforced section, over reinforced or balanced section, the strain in steel must be large extent at the time of failure. Sometimes in examination, the numerical question may be, what is the strain at the time of failure for Fe 500 grade steel? So Fe 500 means put Fy equal to 500, Es equal to 2 into 10 power 5, and find out the strain. And find out, sometimes such a simple questions may be asked in the examination. So strain in steel should not be less than. Normally should not be more than is the generalized concept. Stress should not be more than some value. That is a generalized concept. But here it is a reverse. Strain should not be less than this magnitude. That means when the strain is more than this value, then ductility property imparted to the concrete. And at the time of failure, because of the deformation, more deformation, it will give advance warning before failure. So we can predict the structure is going to fail by means of some deformation things. Now, failure in this particular limit state method, failure of the member is always ductile in nature, because strain in steel is not less than certain value. Okay, and because of this assumption, neutral axis depth is limited. It restricts the depth of the neutral axis, because you know that in the limit state method there is a term XU maximum. That means XU cannot be more than XU maximum. XU maximum itself means depth of the neutral axis maximum. Maximum depth of the neutral axis is a certain value that is limited. That is limited. So because of that assumption, it restricts the depth of the neutral axis, which we normally call it as XU maximum. And sometimes this may be the question in the exam. Don't by heart. For Fe 250 grade steel, what is the maximum strain at the collapse? Strain at the collapse should not be less than Fy by 1.15 ES 0.00 to 0.0038. So this is the strain in steel reinforcement at the time of failure. This is the strain in steel at the time of failure in M20 Fe 250 grade. So for Fe 250 grade, this is the strain. But what is the strain at the time of attaining the design stress? Already have seen another one. Here for Fe 250 grade, strain at the design yield stress is only 0.00109. That means when the strain reaches 0.109, you will get 217.5 Newton per mm square. But sometimes that means the curve will be like this up to this straight line, and afterwards elongation any amount of elongation will give you advanced deformation only. There is no increase of the stress, but this value is 109, whereas the strain in actual steel of Fe 250 should not be less than 00308. That means here FD value of 0.87 times of 250 is already available. So here, particularly for the case of mild steel, we should not worry about anything. You always substitute the value 0.87 times of 250. Whereas in case of Fe15 or Fe500, the stress magnitude depends on the strain. So here what is the value? ES is not less than this much. So this much is 380. You can look at the table. In the 380 means it's the last value. When it is last value, then the stress will be 360. If the strain is less, what is going to happen? Stress is also less in the material. And similarly for 500 grade, this is how it is computed. The minimum strain at collapse ensures that the design stress in tensile steel at collapse is always FYD. And for mild steel, the corresponding value is 0.00109, and naturally in this particular assumption, it is considered that when the strain should not be less than 0.0038 in case of mild steel. But at the smaller value itself, its yield value occurs. So that's why without any hesitation, for mild steel, it is always to be considered as stress equal to 0.87 times of Fy. So these are the various assumptions that are considered as per IS 456. So don't worry about this table. It is only the computation of the strains shown at this level. So sometimes if there is a small question, a numerical question regarding the computation of the strain and also associated stress in steel, you can understand how to calculate in the examination. Okay. Now let's go for singly reinforced beams. So all assumptions are over now. So based on all assumptions, now we are deriving the various equations related to the singly reinforced section, or otherwise we can call it as stress block parameters. Now understood this particular diagram first, and this diagram is more important. If you understood each and every letter and also the line in the diagram, then this is more than sufficient for getting all the subsequent calculations. P is the width of the beam. Capital D is the overall depth of the beam. Small d effective depth of the beam. Effective depth means distance of the centroid of the steel reinforcement from the extreme compression fiber. This is the compression fiber and this is the centroid of the steel. So distance between the centroid of the steel reinforcement to the extreme compression fiber. And this is the strain diagram. Already you know, based on the first assumption itself, the variation of the strain is linear across the cross section. When the strain is linear across the cross section, and this is another assumption that maximum compressive strain in concrete is taken as 0.0035. Maximum strain in concrete is taken as 0.0035. This is another assumption. And what is another one more assumption? The strain in steel should not be less than. You know that it is strain in steel epsilon s should not be less than 0.002 plus Fy by 1.15 s. Just now you have seen this is another assumption. So that means in the strain diagram, at the top it is 0.0035, at bottom it is 0.002 plus Fy by 1.15 s, and x is the depth of the neutral axis. Now we call it as xu. xu is the depth of the neutral axis. And below the neutral axis, the distance of the steel reinforcement is d minus xu. So this is the regarding strain. So what you need to understand here, what is the strain at the top, what is the strain at extreme bottom, what is the depth of the neutral axis, what is the remaining distance. Only these four parameters are important. Now this is called the stress diagram, or we can call it as a stress block. So stress block already for concrete, what is the final stress diagram? It is varying. It is varying up to a curve. It is varying up to a curve, and afterwards it is a straight line. You know that final one is 0.45 FCK. 0.45 FCK. This is 0.002, 0.0035. Already I have seen earlier in this is one of the assumption. So now you can look at this is the neutral axis where it is 0, and then it is parabola, and afterwards rectangle, and this is called the exactly the stress diagram given as per the IS 456. So the maximum value, what is the maximum value? It is 0.45 FCK. 0.45 FCK, and if you want to go a little bit more accurate, 0.446 FCK, and nothing wrong in that. Okay, and here this is entire concrete under compression. Concrete under compression will resist the compressive force. So because of this entire concrete, the resistance of the concrete is by means of C. Resistance of the concrete is nothing but C. C is the compressive resistance. And similarly, because of the steel reinforcement, the tensile resistance of the steel reinforcement is T. And T means stress multiplied by area. So here what is the design stress? 0.87 Fy is the design stress multiplied by AST. And what is the design compressive force? The design compressive force is area of this stress block multiplied by corresponding area of it. Already you know how to calculate C in working stress method. There also average area multiplied by the area of the concrete. So here also the same concept is being used for computing the C value. So here the C value is because of the two parameters. Because of the two parameters. So one parameter is because of the two parameters. One parameter is the rectangular portion. So you can call it as C1. C1 is the compressive resistance provided by the rectangular portion of the stress block. Another force will be C2, compressive resistance provided by the concrete corresponding to the parabolic stress block is C2. And some of these two will be acting at somewhere here, which is C. That C is called C1 plus C2. That C is called C1 plus C2. So this C is nothing but sum of C1 and also C2. That means compressive resistance of the rectangular portion plus some compressive resistance of the parabolic portion of the stress block. So another important point here is XU is the depth of the neutral axis, and already I told you the top is 3 parts because it is 0.002, whereas it is 0.0035. Total is 7 parts, and out of 7 parts, first is 4 parts, next is 3 parts. So 3 is rectangle. So you can write 3 by 7 of XU. Sometimes the question may be, what is the depth of the rectangular portion of the stress block? What is the depth of the rectangular portion of the stress block? 3 by 7 of XU. If you simply by heart 3 by 7, 4 by 7, it is always under confusion. But if you remember this strain diagram, up to here it is 7 parts. So up to this it is only 4 parts, remaining 3, so that you can understood that it is 3 by 7 of XU, and similarly the other one will be 4 by 7 of XU. So do not try to by heart any of the parameter in the diagram. Always understood the clear concept of the parameters, then only you can answer in the examination. And the questions sometimes are very small, very small. Very small means simply what is the maximum strain basing on this. What is the maximum strain and compression? What is the depth of the rectangular portion of the stress block? What is the depth of the parabolic part of the stress block? Like that, very small questions may be asked in the examination. Now look at already I told you C1 and C2. C1 is compressive resistance due to rectangular portion of stress block. So what is compressive resistance? First, compressive force. What is compressive force? Height is, what is height? 3 by 7 of XU. What is width? 0.45 FCK or 0.446. So width and height. So this is area of the stress block. Area of the rectangular portion of the stress block is 0.446 FCK width, and 3 by 7 XU is height, multiplied by the area. What is the associated area here? The associated area will be B. B. Because already XU is taken into account, and what is the width? Width is nothing but B. So multiply all these things, you will get 0.191 FCK B into XU. So this is called the C1. Sometimes in the examination, this may be the question. But don't remember 0.191, because when this question asked, so you should be able to get this multiplication within few seconds. You don't try to remember 0.191, 0.169. It is always confusing if you remember more and more values of this, because we do not know whether this question is going to come in the exam or not. If the question comes in the examination, then your mind should move towards this diagram and accordingly get the final value. Next, C2. Compressive resistance due to parabolic portion of the stress block. And you know, this is the parabolic portion. Parabolic portion height is 4 by 7 XU. What is the width? Width is 0.45 FCK. What is the area of the parabola? Area of this parabola is 2/3 of base into height. 2/3 of base into height multiplied by the entire width. Multiplied by B, it is 0.169 FCK B into XU. So you got C1 and also C2 both. C1 and also C2. What is C? Sum of the two. C means total compressive resistance of concrete, C1 and C2. C1 is that, C2 is that, and C is this. But you need to remember this. It's not remember by repeated reading automatically. It is definitely there in your mind. 0.36 FCK B into XU is the compressive resistance of the concrete. And how you got this C value? This C value is basing on the 2/3 of FCK. Originally FCK, and we are considering the size effect, and it will be reduced by 2/3 of FCK, which is 0.667 times FCK. And afterwards, it is again applied with the partial safety factor of 1.5, then it will be 0.5 FCK. That means when it is 0.5 FCK, it is 0.36 FCK B into XU. Sometimes in the examination, if they want to test your knowledge, instead of 1.5, if it is say 1.25, if it is 1.25, what is the value of the C? That may be the question sometimes. In that case, what you do? 0.67 is original. Instead of dividing by 1.5, you are going to divide it by 1.25 and find out the value. The question in the examination is based on testing of your conceptual knowledge. Testing of conceptual knowledge. The question is, instead of considering the partial safety factor for concrete as 1.5, let us assume that as 1.25. So then what is the compressive resistance of the concrete? And this formula is not valid. This formula is valid when it is 0.45. Here top compressive stress is 0.45 FCK. When it is not 0.545 FCK, the total compressive resistance is not this. But this value is correct as per IS 456. But in the examination, the questions may be asked anyway. You should be able to solve it by fundamental computation. Right? Now T, tensile resistance of concrete. Already I told you this is a stress in steel and also area of the steel. So in the diagram, you can look at C means 0.36 FCK B into XU. 0.36 FCK into B into XU. There is no maximum. 0.36 FCK into B into XU. And what is T? 0.87 times Fy into AST. So with this, the total concept regarding the singly reinforced beam is over. And accordingly, you can calculate some of the things further. What are the some of the things? Because you know C1 is at one point, C2 is at another point. Resultant is C. What is the distance of resultant from the top? Distance of the resultant from the top is say A. So that means the total compressive force is acting at a distance of A from the top fiber. So how to calculate this center of gravity? You know C1, C2. So C1 Y1, C2 Y2. What is where it is C1? C1 will be half of the total depth. What is the total depth? 3 by 7 of XU. 3 by 7 of XU means this will be acting half of 3 by 7. So what now you do is A means distance of the compressive force from the extreme compression fiber. So C1 A1 C2 A2 by C1 plus C2. Already you know C1. And what is A1? A1 is half of 3 by 7 because it is rectangle. Because it is rectangle. And C2 multiplied by this is the some distance. What is that distance? You can look at C2 is somewhere here. So part of it, this distance, this distance plus rectangular distance. You know rectangular distance is 3 by 7 of XU plus part of it. What is that part of it? You can look at here. 3 by 7 of XU rectangular plus 3/8 of 4 by 7 XU. So normally for parabola, if this is parabola, center of gravity is here. This is nothing but 3 by 8 of height, whereas this is nothing but 5 by 8 of height. So we need the center of gravity from top. It is 3/8 of 4 by 7, and substitute this. And the computation of 0.42 XU. So A is 0.42 XU. So this is called the distance of the compressive force from the extreme compression fiber. Now, what is lever arm? So lever arm means the distance between the compressive force and tensile force. This is called the lever arm. Already I told you earlier in working stress method of design, Z is the lever arm, which is the distance between the center of gravity of the steel reinforcement to the center of the compressive reinforcement. So distance between C and D. So what is the Z value? From steel up to top it is D minus what is this distance? 0.42 XU. So Z is nothing but now D minus 0.42 XU. D minus 0.42 XU. So these are the major parameters. Now, like working stress method, here also the different types of sections are there. Under reinforced section, balanced section, and also over reinforced section. And whatever the concepts that we studied there are valid here, and the same concept, same thing. For example, in under reinforced section means reinforcement is low and stress in steel reaches early, so steel fails. So similarly, over reinforced means the over reinforcement means reinforcement is more than the required. So concrete is weak, concrete fails. So then that is called the over reinforced section. Balanced section means both the steel and concrete simultaneously fails. That is called the balanced section. And whatever the points that discussed earlier, the same points are valid regarding these three different types of sections. And here comparison of identification of the different types of sections based on the depth of the neutral axis. And sometimes if comparison is with moment of resistance, then you can look at mu is less than mu limit. We will see what is mu limit, etc. Mu limit means limiting moment of resistance. If mu is less than mu limit, it is under reinforced section. Mu is equal to mu limit balanced section. Mu is greater than mu limit. This is called over reinforced section, but this is always to be redesigned. I will explain a little later in the next part. Now, another important part is XU maximum. So normally what you do, to find the different types of sections, XU depth of the neutral axis is always compared with the XU maximum. So if you want to compare with the same XU maximum, you need to find out. So how to find out this XU maximum? Here also don't by heart anything. According to the requirement in the examination, you need to calculate it. This entire calculation is as per the IS 456. So you know this is the strain diagram. It is XU. This is D minus XU. Top is 0.0035. Bottom is 0.002 plus Fy by 1.15. Yes. That's all about the strain diagram. So all these values will be obtained only from those three diagrams. Already you know that there are three diagrams. Everything will be obtained from this diagram only. So keep this diagram in your mind so that you can answer any type of questions. So now for limiting depth of the neutral axis, when you will get limiting depth of the neutral axis will be at balanced section. At balanced section means when 0.0035 and this value both fails simultaneously, both concrete and steel fails simultaneously, then depth of the neutral axis will become XU maximum. This will become XU maximum and this will become D minus XU maximum. So from this diagram what you do? From this diagram what you do? You just see the proportionality of triangles. XU by D minus XU. You know this is XU divided by D minus XU equal to corresponding to XU, top is 0.0035 and bottom is 0.002, etc. So now simplify this. How to simplify this? Numerator is adding to the denominator. XU is adding to the denominator. So XU is same, and if XU is added to the denominator, D minus XU and that XU will get cancelled, you will get only D. The same thing is to be applied other side also. So numerator is same, it is to be added to this, so that will be 0.0055 and Fy by this one, and so that XU will be equal to multiplied by D. That means XU value depends on Fy, type of steel, and of course modulus of elasticity is the same for all the different types of steels. So for different grades of steel, the different limiting depth of the neutral axis. So when the strain in concrete and strain in steel reaches maximum value simultaneously, what is going to happen? XU is going to become XU maximum. So XU equal to this equation. Don't remember anything. Always try to evolve or write the equations as per the requirement in the examination. And for Fe 415 grade steel, in the previous equation, Fy 415 and modulus of velocity 2 into 10 power 5. If we calculate this value, this entire thing is 0.48 T. So now XU maximum equal to 0.48 times D for Fe 415 grade steel. So in the same way, you can compute for 250, you can compute for 500 also, and accordingly 0.53, 0.40, 0.46D are the limiting depth of the neutral axis for different grades of steel. So you have to remember this. You have to remember this because these are the standard steel reinforcement. Sometimes numerical question: what is the limiting depth of the neutral axis for Fe 500? That may be the question. So you need to answer 0.46D. Or if the question is this 0.48D, or for Fe 250 it is 0.53D. So you have to remember this. But this entire procedure I have given, I will tell you that a little later. I'll tell you okay, I'll tell you now only. Why I am telling all these things? I can simply say these three are the simple values. Uttarvadan. These three are the simple values that you can by heart, that I can tell. But sometimes in the examination, the questions may be concept oriented testing. The questions, how the test questions will be, I'll tell you this. For example, what is going to happen is in the examination, whether you know this entire concept of learning or not, they will test. The question will be something like this: assume that the concrete is strained to 0.003, whereas at the bottom it is 0.002 plus the same thing Fy by 1.15 yes. So that means strain in concrete is not 0.0035 as per the code. As per the code, if it is 0.0035 and as per the code, strain in steel is also this, then only this combination of the values are valid. This combination of the values are valid. If the strains are different and that value is not the same, you have to compute the value in this particular manner and the value is something different. Question, how the question will be, instead of taking maximum strain in concrete as 0.0035, now it will be considered as 0.003. Then the depth of the neutral axis, limiting depth of the neutral axis for Fe 415 is. That may be the question. I will explain some of the numerical examples later, and because of such a numerical questions in the examination, I am giving more concepts, detailed concepts in discussion. Otherwise, I can finish the same. I can finish the same by telling only 0.53D, 480, 460. That will not serve for the overall purpose of understanding the total knowledge. Okay. Now, limiting depth of the neutral axis corresponding to the balanced section or balanced failure of the limit state of flexure. Okay. So now here there are different types of sections. If already now you know XU maximum value, XU maximum value. So XU is the actual depth of the neutral axis. Like working stress method of design, XU is the actual depth of the neutral axis here. When XU is less than XU maximum, that section is called the under reinforced section. When the section is under reinforced, tension failure occurs. Tension failure occurs. When XU is more than XU maximum, the section is called the over reinforced section and accordingly compression failure occurs. Compression failure, whatever the discussion we had earlier in working stress method of design, the same is valid for the type of beams in limit state method of design also. Now what is tension failure? You can look at, already I told you, but anyway let us have a small discussion. Tension steel yields before ultimate strength is reached. So first tensile steel yields, then beam undergoes considerable deformation because the steel is going to fail, and steel fails only by giving proper deformation, considerable deformation, and because of giving deformation of steel, extensive cracks will be there in concrete before failure. So that means we can observe that the structure is going to fail. So that means we are getting some advanced warning that the structure is going to get damaged because of the tension failure. And large strains develop in tension steel, and hence extensive cracks develop in concrete. Because of extensive cracks developed in concrete spalls out and all other problems will be there. So you can identify that the structure is going to fail if it is under tension failure. Whereas in case of compression failure occurs only when concrete fails. And tensile steel does not yield ultimate strength is reached. The failure is sudden since concrete is brittle. So these are the generalized statements when pure compressive failure occurs. But in the limit state method of design, one of the important point is whether concrete fails or steel fails, the strain in steel is not less than 0.002 Fy by 1.15. Yes, that means whether the failure is concrete or the failure is by means of the steel, strain should not be less than this value. That means whether concrete fails, steel automatically fails. Whether steel fails, automatically steel fails. So in the limit state method, the nature of the failure is always ductile in nature. It is unlike working stress method. In working stress method, there is a possibility of pure compressive failure. But here, compressive failure may occur, but compressive failure along with the tensile failure of the steel reinforcement also occur simultaneously. Okay. Now, limiting moment of resistance. So here in the previous case, limiting depth of the neutral axis. Once the depth is limited, moment of resistance also limited. So that's why it is called limiting moment of resistance, and the symbol associated with this as per the code MU limited. MU limited, ultimate limited, ultimate limiting ultimate moment. Limiting ultimate moment of resistance. So limiting moment of resistance occurs at the balanced section. You know, at the balanced section, x is equal to xu maximum. So what is the formula in this? What are the formulas that are there here? What are the various formulas in general? The various formulas in general that I'll tell you. Okay. So this is now limiting moment of resistance. You know, the moment of resistance, if it is failed by means of steel, it is T into Z, or what is T into Z? 0.87 Fy into AST into D minus 0.42 XU. That's the formula. If the moment of resistance is by means of compression, it is nothing but 0.36 FCK P into XU into D minus 0.42 XU. These are the only formulas available. You know what is C? C is nothing but 0.36 FCK B into XU. What is T? 0.87 FYAST. And in both the cases, Z is D minus 0.42 XU. So this is how the moment of resistance normally computed for under reinforced section and also the over reinforced section. Now we are calculating the limiting moment of resistance. Limiting moment of resistance will occur when actual depth of the neutral axis is equal to limiting depth of the neutral axis. So in this case, what you do, mu limited equal to, you know, mu. When you will get 0.36 FCK B XU, wherever XU is there, put that XU maximum. Again, D minus 0.42 XU, you can look at here, D minus 0.42 XU. Here also you are using 0.42 XU maximum. What is XU maximum for Fe 415 grade? For Fe 415 grade steel, what is that? 0.48D. Already we have seen it. For Fe 415 grade steel, 0.48D is the XU maximum. And substitute that value here, 0.48D, here also 0.48D, and multiplication of these, you will get it 0.138 FCK BD square. In working stress method, you have seen it as RBD square. RBD square. Now it will be 0.138 FCK BD square. So this is for Fe 415 grade steel. Similarly, if you substitute XU maximum equal to 0.53, 0.53D, then you will get 0.148 FCK BD square. And if you substitute XU maximum will be equal to 0.46D, you will get 0.133. So for different grades of steel, you will get a different limiting moment of resistance, 0.148, 138, 133. You have to remember this. Automatic remember, not by hearting. 0.148, 0.138, 0.133 FCK BD square according to the various values. Sometimes if you forget this, don't worry about it. What you do, mu limit will be, you know, this always this equation, and in that equation substitute XU value by XU maximum, you will get the corresponding value. Then limiting percentage of reinforcement. So why limiting all? Limiting depth of the neutral axis is the corresponding to the balanced section. So for balanced section, we are computing in the previous section moment of resistance. What is the moment of resistance for balanced section? That will be, these are the values. These are the values for the moment of resistance for balanced section. Similarly, for balanced section, what is the percentage of steel reinforcement? For balanced section, what is the percentage of steel reinforcement? For that, it is limiting percentage of tensile steel reinforcement. PT limited. P is percentage, T is tensile steel, and limited means for balanced section. Percentage of steel reinforcement at balanced section. And you know that C equal to T. What is C? 0.36 FCK B into XU. XU is general. But since it is balanced, instead of XU, now we are using XU maximum. And remaining same, 0.87 FY AST, everything same. And from this particular equation, AST by B, you know this AST, you know here B. So AST by B, it can be written in this way. 0.36 FCK by 0.87 FY into XU maximum. Normally, what is the percentage of steel reinforcement? Percentage means AST by BD into 100. This is called the percentage. AST by BD into 100. But in the formula, you know, AST by B. AST by B. But here BD and here also multiply it by D. So you can look at this can be written as by multiplying both of the sides, here D and also here D. So 0.87 Fy and here also XU maximum divided by D into 100. So ultimately this is a simplified value. Don't by heart this. Don't by heart anything. This is the original equation everybody knows. If at all a question in the examination, you always try to calculate any value from the base. Don't remember this. If you try to remember this, you will forget definitely 100%. So now XU maximum term is involved. How, on what factors XU maximum depends? XU maximum will be equal to 0.53D, 0.48D and 0.46D. 0.53D for Fe250 and it is for Fe415 and it is for Fe500. If you substitute these values, you will get appropriate percentages. Okay, sometimes in the examination, the question is, what is the limiting percentage of steel reinforcement for Fe500 steel? 500 steel. In that case, what you do? Here Fy500, you put here itself, Fy500 and XU means 0.46D, 0.46D and FCK some given value, so that you will get percentage here itself only. So now, basing on the percentage also you can decide what is under reinforced, what is over, what is balanced. If the actual percentage of steel reinforcement is less than the limited, it is under reinforced. If the actual percentage is more than the limited, over reinforced section. If both are equal, it is called the balanced section. It's called the balanced section. Now coming to this, moment of resistance increases as percentage of steel reinforcement increases up to the balanced section and thereafter. Okay, based on this previous discussion and also XU limited in the formula you can look at MU limited. This is for the balanced section. For balanced section, XU is substituted as 0.48D and it is balanced. If it is over reinforced, what is this value? What is the value of XU for over reinforced? For over reinforced also the same value. The same value. That means moment of resistance of the balanced section or over reinforced section is one and the same. That means any increase of steel reinforcement will not increase of the moment carrying capacity of the section in a limit state method of design. The case is different in working stress. In working stress method of design, as the steel reinforcement is more and more, and till concrete is able to take the load, then the moment of resistance is continuously increasing. Whereas in this case, once the steel reinforcement reaches to its limiting stage, any additional quantity of reinforcement provided, there is no improvement in moment carrying capacity of the section. And don't think that more reinforcement keeping in a member will increase always. No, it is not. So up to balanced section only, the steel reinforcement will be increasing the moment carrying capacity. Afterwards, it is constant only. So you can look at this. This is the original formula, and for the balanced section, you are substituting 0.48D, and for over reinforced also the same thing, because XU is becoming XU maximum. Why it is called maximum? Though the reinforcement is more, this XU is not going to increase. It has its own limiting value. That is called XU maximum. That's why moment carrying capacity at balanced section and over reinforced section is one and the same. So for that you can look at the diagram. Percentage of steel. As the steel increases, the moment of resistance also increases up to the balanced section. So this is this is called percentage of the steel limiting. Percentage of steel limiting. This is the limiting percentage of steel reinforcement. That means steel reinforcement percentage required for balanced section. After that, if you put even double the quantity of reinforcement, is there any improvement of the moment of resistance? No, it is straight line only. Straight line only. There is no increase in moment of resistance. That means in limit state method of design, the reinforcement can be provided up to the limiting percentage. Beyond that, if you provide any amount of steel reinforcement, it is not of any use. There is no use at all. There is no use at all. Then there is no moment carrying capacity of the increase. There is no increase of moment carrying capacity. Okay. Now let's look at problem. For M20 grade of concrete and Fe 415 grade steel, what is the percentage? That may be the question in the exam. For that, don't try to remember this equation. Don't try to remember this equation. That is this one, last one, 41.38. This equation is for computing the percentage. Not required. Don't remember. So what you do, you know fundamentally this equation 0.36 FCK B XU. What is XU? XU is nothing but XU maximum. 0.87 FY AST. If you substitute all this, you know here B and D, you know AST. So AST by BD and all other numerical values, you will get 0.0096. AST by BD. What is percentage? AST by BD into 100. That means this value multiplied by 100. So 0.96. So sometimes the question may be in the exam, what is the percentage of steel reinforcement at the balancer section for M20 grade of concrete and Fe 415 grade of steel reinforcement? Answer is this. So to get this answer, you don't remember any of the final formula. This is not at all a formula. Formula is only at the beginning concept. Beginning concept. Okay. Now it's over. Now types of sections. There are three different types of sections. One is one parameter XU, another parameter is XU maximum. XU maximum is 0.53D, 0.48D, 0.546D. It depends on the different grades of steel reinforcement. XU means actual depth of the neutral axis. So here actual depth of the neutral axis is to be found by equating the compressive force and tensile force. First you should identify whether it is under reinforced section or over reinforced section. To identify the under reinforced section, use C equal to T. C 0.36 FCK BXU, T is 0.87 FYAST, and knowing all values, find out XU. That means quantity of steel reinforcement is known, width of the section is known, grade of concrete is known, grade of steel also known, only XU is unknown. You can find out XU value. This is the prime, and in the examination this may be the question in the exam. Some data given, the depth of the neutral axis is, that may be the question. So simply equating C and T, you will get the actual depth of the neutral axis. Once XU is known, find out XU maximum by knowing the formulas 0.53D or 0.48D or otherwise 0.46D depending upon mild steel, Fe415, Fe500. And now compare the values of XU and also XU maximum. If XU is less than XU maximum, the section is under reinforced. The same concept as that of earlier. Then what is moment of resistance? Tensile force multiplied by Z. Tensile force multiplied by Z. What is tensile force? 0.87 FYAST T minus 0.42 XU. So this is the formula that is to be remembered. That is enough. This is the only thing. What is this formula? Don't remember this formula. What is this formula? XU. What is XU value? XU from here is, you can look at it. XU equal to 0.87 Fy AST by 0.36 FCKB. That is called the XU from here. If you substitute this XU value here, you will get this equation. You will get this equation. No need of remembering, because you know XU value, you know this equation, and if required, you substitute XU value here, automatically you will get this equation. So in the examination, the question may be, what is the depth of neutral axis? Or another question, what is the type of section, whether it is under reinforced or over reinforced? Another question, what is the moment carrying capacity of the section? So these are the three possible questions. It is under reinforced. Next one, if XU is more than XU maximum, the section is over reinforced section. When it is over reinforced section, moment of resistance is C into Z, and XU will become XU maximum, because even the value of XU is more, XU value is going to be limited. For example, XU will be equal to 235 and XU maximum will be equal to 188. So what you will do, this is clearly over reinforced section, because XU is more than XU maximum, but now XU is limited as XU maximum, which is 188 for all calculations. XU equal to XU maximum, which is equal to 188 for all calculations. We should not use 235, because the depth of the neutral axis is limited. That is limited because of the strain condition. One of the assumption is strain not less than 0.002 plus Fy by 1.15 ES. So because of that condition, it will be this. So what is that you are going to get? 0.36 FCK B. In place of XU, it is XU maximum. T minus 0.42 XU maximum. That means this is same as that of balanced section. So when it is over-enforced section, either you substitute here XU maximum or otherwise these standard values 0.148, 138, 133, this can also be used. That means moment of resistance of a balanced section or moment of resistance of a over-enforced section is one and the same. I will read one line. Moment of resistance of the over-enforced section is equal to that of the balanced section, since the depth of the neutral axis is limited. Okay, so that means in this particular limit state method of design, you have ultimately two computations: moment of resistance for balanced section, moment of resistance for under enforced section only. Next, of course, XU equal to XU maximum, it is balanced section. Either it is with CZ or multiplied by TZ or otherwise these formulas. So whenever it is balanced, the limiting values are always corresponding to the balanced section. Okay. For balanced section, steel may mitigate failure. Steel may mitigate failure, but collapse of the structure is due to crushing of concrete. So, here in under reinforced section, steel fails. In over reinforced section, concrete fails. In balanced section, here also steel fails, but steel and concrete both fails. But the type of when concrete is going to fail, it is always sudden. Though the failure is by means of mitigating the steel, the crushing of concrete will be taken place, and balanced section also fails by means of crushing. So that's why the design of the sections must be for under reinforced section only. Balanced sections are not advisable for design since it causes sudden collapse by crushing of concrete. So XU maximum depends on the grade of steel only. XU maximum and it is independent of grade of concrete. You know, XU maximum will be equal to 0.48D. 0.48D. So how you got this? It depends on only the steel reinforcement. It is for FE 415 and irrespective of the grade. For any grade of concrete, if the steel is Fe 415, XU maximum is 0.48D. So that's why it is independent of the grade of concrete. Now, tension reinforcement. Normally, for a beam, for example, if it is a simply supported beam, the tension reinforcement will be provided on the tension face. This is called the tension reinforcement. And as per the design, you will get some quantity of steel reinforcement. That should be more than the minimum value. That should be less than the maximum value. So here, code requirement has given minimum quantity of reinforcement. Minimum reinforcement is given by AS by BD 0.8 by FY. So this is the formula in the code. You have to remember this. AS by BD 0.85 by Fy. AS is called the minimum area of the tension reinforcement. B width of the beam. D effective depth of the beam. Fy character. All parameters are known. So here sometimes the question may be asking what is the minimum area of the steel reinforcement. That may be the question. Or sometimes what is the minimum percentage of steel reinforcement. What is minimum percentage of steel reinforcement? Minimum percentage of steel reinforcement, you know, here AS by BD. AS by BD is nothing but the percentage. You can write here AS by BD into 100 is nothing but P, percentage. What is percentage now? It is nothing but 0.85 by Fy into 100, which is nothing but 85 by Fy. So if the question in the examination, what is percentage means 85 by Fy. If it is 250, put 250 or 415 or 500 or any grade of concrete. So according to the requirement of the question, what is the minimum area of the steel may be the question. What is the percentage of steel reinforcement may be the question. you need to remember this particular formula. Okay. And why minimum reinforcement is required? Why minimum reinforcement required? You will get certain reinforcement. For example, here you will get 220 millimeter square. 220 millimeter square. But minimum value is say 235. So what you have to do? You have to use minimum value of 235 and not as per the design. So the design value should always be more than the minimum value. So why minimum value is provided? If the minimum steel reinforcement is not there, what is going to happen? Sudden collapse occurs due to breakage of bars, because reinforcement is going to be very small and breakage will occur, and hence sudden collapse may occur. So that's why code has recommended minimum grade of steel reinforcement on tension phase. And at the same time, code also has given maximum reinforcement, limit. Or if you calculate the AST, that should not be more than maximum value. That should not be more than the maximum value. So maximum reinforcement also has some limitation. What is that limitation? Maximum area of tension reinforcement shall not exceed 0.04 BD. B is width and capital D is the overall depth. What is the meaning of it? Maximum area of tension reinforcement should not be more than 4% of, here it is there, 4% of gross cross-sectional area. Gross cross-sectional area. Effective cross-sectional area means B small d. B small d is the effective cross-sectional area because D is effective depth. But here calculation is B multiplied by D, so that it is called the gross cross-sectional area. So maximum area of reinforcement is 4% of the gross cross-sectional area. The limit of maximum steel reinforcement, why it has been limited? It is mainly, the major problem is placing of concrete and compaction of the concrete between the bars is difficult. If too much of reinforcement is provided, then placing of concrete, compaction of concrete is difficult. Form work is also difficult. That's why code has given the maximum limit of the reinforcement. So sometimes the questions in the examination may be, for FE 500 grade steel, minimum percentage of steel is. Minimum percent. Minimum means you remember this formula. So in this, AS by BD into 100 is P. So 8.85 by Fy into 100, and it is nothing but 0.85 by 500 into 100, 0.17. Don't by heart. And sometimes the question may be for 415, for question may be for 250, question may be for 550 also. So accordingly substitute and get the percentage of, minimum percentage of the steel reinforcement. Okay, I will spend another 5 minutes and I will close today. Another 5 minutes. Nominal cover to the reinforcement. Nominal cover to the reinforcement. We can normally call it as cover to the reinforcement, clear cover to the reinforcement, nominal cover to the reinforcement, all are one and the same. So nominal cover is depth of concrete cover to all steel reinforcements including links. So you can look at nominal cover or clear cover is this. What is that clear cover? You can look at here the distance below the link. The distance below the link to the extreme point is called the clear cover. This is not the bottom of the main bar. It is bottom of the link. Bottom of the link to the bottom of the section is called the clear cover. Is called the clear cover. What is effective cover? Effective cover is from extreme tension phase to center of the reinforcement. That is called the effective cover. And as per the code, for different members, slab 20 mm, beam 25 mm, column 40 mm, footing 50 mm. So these are the cover minimum cover to be used for various types of structures. Sometimes the question may be, what is the minimum cover to be used for column? That is, answer is 40, or for footing answer is 50 mm. So that is to be that is a type of question. So here the terminology is clear cover, effective cover. Effective cover is for one layer of reinforcement. Sometimes if two layers of reinforcement exist, the center of the space to the bottom, center of the space between the two layers to the bottom is called the effective cover. And normally this cover also, more cover is required depending on the type of exposure. Sometimes the structures are extreme exposure. Extreme exposure means when the structures are constructed on the offshore or otherwise offshore structures. For offshore structures, the minimum cover to be used as 75 millimeters. Nominal cover not less than. In the previous case 20, 25, 40, all those are ruled out. When it is mild only, 20 mm is the minimum cover. And for all other environmental cases, or buildings, or sometimes buildings constructed in chemical factory where more chemicals are exposed, depending on the environment, the cover to be used as maximum. And similarly, for main reinforcement up to 12 mm diameter for mild steel exposure, nominal cover may be reduced by 5 mm. So normally for mild exposure it is 20 mm is the minimum cover. If the diameter of the bars are 12 mm or less and the exposure is mild, 5 mm may be reduced. That means instead of 12, it can be 5 mm also, provided the diameter of the bar must be 12 mm or less than that, and exposure must be mild. Similarly, for exposure conditions severe and very severe condition, reduction of 5 mm may be made when the concrete grade is M35 and more. So for severe case and very severe case, if the grade of concrete is M35, M40, M45, etc., you can reduce 5 mm. That is 45 minus 5. You can reduce it to 40. Actual concrete cover should not deviate from the required nominal cover by 10 mm. That means, for example, for column, 40 mm is the normal cover. You can go up to additional 10 mm, 50 mm, but you should not go beyond that unless it is clearly specified. In case of columns, minimum dimension of 200 or less, whose reinforcing bars are 12 mm nominal, 25 cover may be used. But for normally columns, 40 mm. In general, columns clear cover is 40 mm. But if the column size is very small, 200 by 200 or even less, and at the same time 12 mm bars are used, this can also be reduced to 25 mm as clear cover. So like that, certain things are there. One or two examples, I will close it. When the thickness of the slab is 150 mm, area of steel reinforcement is 10 mm 150 as main reinforcement, 10 mm 8 mm 100 as distribution reinforcement. Exposure is mild. The question in the examination is, what is the minimum nominal cover? Minimum nominal cover. Already I told you, for slab it is 20 mm. But here, depending on the condition, what is that condition? If it is less than 12 mm and mild exposure, 5 mm can be reduced. So minimum clear cover must be 15 mm only. This may be sometimes confusing questions, because slab means everybody will go that it is 20 mm, but it is not 20 mm. It is depending on the type of exposure and the diameter of the bars to be used. the diameter of the bar is less than 12 and size of the member is this and exposure is mild, then 5 mm reduction can be allowed. Similarly, for M40 grade of concrete in severe environment, what is the minimum cover? You know, in severe environment, 45 mm is the cover. But when you use M30 and above M30 grade, 5 mm can be reduced, so the minimum cover will become 40 mm. Minimum cover will become 40 mm. Like that, you can compute the various values of the cover. Okay. Right. Another 1 minute. For example, if the size of the column is 180 by 180, that is 200 less than 200, and diameter of the bars also 12 mm. What is the minimum cover? 25. Because column means in general 40 mm. But if the size of the column is less than 200 mm and steel reinforcement is 12 mm or lower, then clear cover must be 25 mm. And similarly, another example, size of the beam is say 250 by 650 and steel reinforcement is 28 mm, 3 bars of 20 mm. Stirrups is this type of exposure. The questions are, what is the minimum nominal cover? What is the minimum nominal cover? Minimum nominal cover will be okay, some other values. Okay, we have completed up to this, and tomorrow we are going to study in detail about the numerical problems in tomorrow we are going to study in detail about the numerical problems in singly reinforced beams of the limit state method, both numerical problems and also the questions appeared in previous gate examination. So again, we'll meet tomorrow at 3 o'clock for continuation of this subject. Thank you. Hello. Close చేస్తున్నానండి.